Oh, hey, this one's much better than doing the entire screen. Alrighty then. Alright. So we were talking about magnetic torque. Where's my okay. Alrighty, so I guess the lesson for today is we'll go over what magnetic torque is and properties about magnetic fields that create these magnetic forces, which causes things to torque. And remember, torque is the physics word of saying things that are rotating about an axis. So, we'll introduce this as magnetic torque. Now, the way I like to view torque is things that want to move, things that tend to move because of the energy in the system. And so, with that being said, I'm going to give you a nice analogy of why things torque. So, first of all, if I give you a scenario where you're at a certain height, and then this is a hill, and you drop a ball off a hill, it's going to go straight down because you're in a gravitational field. And so the ball or any sort of object wants to minimize energy. Objects want to minimize energy. So by doing this, this is going to move directly down, and by doing so, it's going to have a potential. A change in the potential is equal to mg h final minus h initial, and since this is, we're defining the bottom to be 0 and the top to be like 10, this is going to be a negative value. It goes negative mg delta h, right? And because this value is negative, that means force gravity pulls you with ease. You're not going against it. Because you're not going against it, the system is at its lowest energy. So the lowest potential is where everything wants to go. And so, in this case, since you guys were talking about torque, you can explain that in a sense about why things move in a rotational field. And so, let's set up a situation where you have magnetic field lines going this way, and you have an object. And you have an object here. Yeah, you have an object here with magnetic moments pointing outwards. And once again, to recap, the magnetic moment is a vector, and the magnetic moment is equal to the number of loops you have times your area vector, and your area vector is of the loop. And this thing right here is actually like a square with area A. And so you're just looking at the direction this points with respect to the current. Now, in this case, since the magnetic moment mu points out of the page, or points to the left, then you know that if you look at a sideways view of this, that current must be going like this. Current goes around this way, and then this is flipped so the magnetic moment points out. That way the magnetic moment comes kind of out like this towards the page. Mu in this case points outwards. Remember, we're using this arrow notation to tell you that it's coming outwards. So mu comes outwards at the page. Well, if you rotate it into back this scenario, that means it points to the left. And so we're going to analyze why this thing torques, or if it does. So torque. So the way I like to think about torque, once again, and I think this is much easier and more intuitive, is it's going to rotate if it wants to minimize energy. So in this case, we'll look at U. U, the magnetic potential, is equal to negative mu, this vector up here, dotted with the magnetic field. And remember, the dot product is the cosine between the angle of the two. Right. And so wants to minimize energy in its orientation. So let's look at this scenario we set up right here. Let's actually calculate this. So we can rewrite this as U is equal to negative mu b cosine theta. And the angle between the two is 180. The arrows point completely opposite to each other. So y'all math whiz know that cosine of 180 is actually negative 1. So U is equal to positive mu b. Well, we just argued, if you look above, that a ball falls. The only reason why a ball falls is because it's moving to a lower potential. So the action of a ball falling is its way of saying it wants to minimize itself. And so by doing that, this potential has to be negative. But we just got a positive value, which means that this orientation right here is not favorable. And the reason why it's not favorable is, once again, the potential is much larger. The potential here is much larger than it is at a different orientation. So let's say if we rotated it, it's rotated 90 degrees. So now we have this situation. To be consistent, I'll draw it in red. B field's going this way, and then now we have it like this. Or we have our object like this, with magnetic moment pointing directly upwards now. We just rotated it this way. Okay, so let's check this out. Because of that, we can use our formula again and calculate the potential is. U mag is equal to negative mu b cosine of theta. What's the angle between the B field and the magnetic moment? It's 90 degrees. Cosine of 90 is 0. Therefore, your potential is equal to 0. That's a little bit better. 0 is still lower than mu b. However, you don't know if that's the minimal orientation or not. So, once again, you want to minimize your potential. And so, let's look at our final scenario, where we have this object now pointing this way its magnetic moment points in the same direction as the B field. So now it moved from here to here. It moved 90 degrees. Okay? So let's check this out. The potential is equal to negative mu B cosine theta. Now, if they're both pointing in the same direction, what is the angle? Theta equals 0. Because theta equals 0, cosine of 0 is 1. And your magnetic moment, your magnetic potential is negative mu B. Now, if you look at the three scenarios, which one has the lowest potential? Well, obviously the one with the negative sign, right? It's the lowest with potential. And so things in nature always want to go towards the lowest potential. They like being relaxed and they like having things, they don't like having an excess amount of energy. They want to always move in the lowest level. And a perfect example is when you throw a ball off a hill. You know, a ball is not going to want to just go upwards. It's not going to, if you just drop it off of a hill, it's not going to magically go upwards because it doesn't want that energy. It wants to get rid of its energy. And the way it does that is it falls. In this case, when you have this object aligned like that, where they're anti-parallel, where its magnetic moment is anti-parallel to magnetic field, then you know that it's going to want to adjust itself to where it has the lowest potential. And the lowest potential is when it's facing the B field. And so you know that it's going to move from this orientation over here. It's going to move 180 degrees to that right there. And so, in order to do that, the thing rotates. Well, this rotation is also known as torque. So, by just looking at the energies, you could realize that, oh yeah, this thing wants to rotate. It wants to rotate because it wants to, once again, minimize its field. And so, to actually find out the torque, we can find out that torque is equal to the cross product of the magnetic moment with the magnetic field. And so, if you look at this, ever so slightly, if you look at this scenario right here, you'll notice, actually, let's look at the first scenario. So the first scenario we have, once again, draw it out, you have the magnetic moment and the B field completely anti-parallel. And so, are you here for tutoring or? So they're completely anti-parallel. So the torque is 0. You know, mu cross B is equal to mu B cosine sine of the angle between the two. Mu B sine theta. Well, theta is 180, so sine of 180 is 0. This thing is going to not torque at this location. So it's semi-stable. Once again, the semi-stable part saying that this thing has higher potential than it would like to be. So you already know, we already deduced by energy that this thing is going to rotate like this. Well, how do we get that? If you slightly move this thing offline, it's going to then rotate. So you just need to give it a little kick. So let's say we actually orientate this thing as in scenario 2, where the magnetic moment is completely perpendicular to the B field. Well, okay then. Well, now the torque is equal to mu b sine of theta, and theta now is equal to 90 degrees. Sine of 90 degrees is 1. So the torque is equal to mu b. Great, but that's the magnitude of the torque. You want to actually figure out that, yeah, this thing's going to rotate like this green arrow over here. It's going to rotate like that. Now, how do you do that? Well, you look at your right-hand rule. So, once again, the way I like to do it is I put my finger on the first vector. I cross it with my middle finger for the second vector, and then the result is your thumb. So, finger, I'll write it in black. Maybe not, I'll write it in blue. Finger is equal to your first vector, or V cross B. Actually, let me do this. I'm going to do it generally so I don't confuse you guys. A cross B. We're going to have finger is equal to A. Then your middle finger is equal to B. And then those give you your thumb, which is equal to C. C is equal to A cross B. So in this case above, A is equal to your magnetic moment, B is equal to the B field, and C is equal to torque. And so, let's look back above. Let's look at this scenario now where they're perfectly perpendicular to each other. If I put my finger in this direction of mu, and then I take my middle finger and I put it in B, then you realize that your thumb has to point in the page. Your thumb has to point in the page, so torque points into the page. If I put my finger up once again, my middle finger to the left points to the right, and then your thumb points inside. And this, I hope you better be doing this with your right hand. That's the only way it can work. And so, you get that the torque's into the page. Well, isn't that what we just figured out? You know that it's going to rotate with this green arrow. And if you curl your fingers by using that same rule, the direction where you curl your right fingers, your thumb points into the page. Again, the direction of torque is the way you curl your fingers. And if you curl your fingers in this green line, you'll get that torque points into the page. Because torque points into the page, you know that it's rotating clockwise. And the object, and in order for the object to have a minimized amount of energy, it will rotate clockwise until it has that orientation where it's aligned up with the magnetic field. And so, yeah, and so that's the way I like to look at torque, because I know a lot of times people get freaked out because of cross products, or get freaked out because it's torque, you know, what do I do about it? Well, the way I like to look at anything from a physics standpoint is, once again, things want to go where it has the lowest amount of energy. So, and everything in nature works like that. The reason why people fall, the reason why things fall, the reason why this thing rotates is because of that also. And so that's much more conceptual for me. If you can also start with your scenario and know that, know that it wants to always line up with the B field. So in order to do that, if you if you slightly move this orientation a little bit from here, then you know that, yeah, the sine of theta is going to be non-zero. And you know that, yeah, it's going to create some torque. And so, with that being said, we can find two interesting things. The work being done is equal to theta 1, theta 2 of tau d theta. You integrate the torque with respect to you integrate torque with respect to theta, and theta is how many radians you went through in a cycle. And so, already sounds good. Well, if you integrate, if you put in our simple equation that we have integral torque times, not torque, we have mu b sine theta d theta, theta 1, theta 2. And if you integrate this, the integral of sine is negative cosine. Negative mu b cosine theta. Theta 1 and theta 2. Oh, gee, that looks a little bit familiar. Well, this is your potential. And it's actually the negative of your potential. And so delta W is equal to negative delta U. And you already knew this from the beginning. You knew from when we learned about electrostatics with electric fields that the work being done to move one charge, or the electric potential, is equal to the negative of integrating that potential energy. And so that's like when you have 2 point charges together, the work, if you have a positive work on moving 2 charges together, that means that, yeah, they're going to be attractive. That means that you're guiding the one particle to move towards the other one. So the potential is lower, right? And so what's interesting about this equation is if we go back to the beginning and we calculated the change of potential, from our orientation where they're anti-parallel, delta U is equal to, well, we just calculated it. Where is it? Yeah, right here. Right here is our final, and our initial, and our final is that. And so you know that delta U is equal to negative mu b. This is U final when they're parallel, when they're both facing the same direction. That's when mu and b are both in the same direction, minus initial, mu b, and this is U initial when they're anti-parallel. And so you get negative 2 mu b. That's your potential. You have a negative potential. So guess what? It's going to do positive work. Well, let's look at our torque equation. Let's say you're going from theta 1 to theta 2. So you're going from, so we already integrated it. So we have negative mu b cosine theta, theta 2 minus theta 1. Theta 1 is, theta 2 is 0. Theta 1 is 180. Right? You start an anti-parallel. So you have negative mu b 1 minus negative mu b negative 1 is equal to negative 2 mu b. Wow, hard to believe that these two values are the same. Yeah, as they should be. Does that make sense? The give me 1 second. Oh, no. Never mind, I screwed up by accident. So the work and the potential should be the opposite. And so, screwed up, and I apologize. Initially, you do 0 radians. Initially, let me just write this out. So, initially, if you look here, you're starting at angle, well, yeah, you do 0, you work through 0 radians. However, at the end of the day, you go through 180 radians, or actually pi radians. So 180 degrees, which means that that's my fault, that you started out at 0 radians, you did 0 radians, and then you slowly move through pi radians. Sorry, so your final is 180, you move through 180 radians, or 180 degrees. Your initial is you move through 0 degrees. So this would get you the opposite of what I had. Right, that would be the opposite of what you have, and you expect the work to be positive. So, my apologies that I said it wrong before. Always delta U should be the negative of the work. And in this case, delta U is equal to negative 2 mu B. The work is equal to 2 mu B. So in fact, that this is the opposite of that value. And since the two are opposites, you know that, yeah, two things could be told with that. A positive work means that the system wants to make you do whatever it wants to do. And in this case, it's going to make you move towards the magnetic field, just like we expected. The potential is negative. The potential is negative because, once again, it did what we wanted it to do, similar to when a ball falls to the ground. Potential is always negative. This potential is negative because, yeah, they're close, and it wants to move that way. And so there we go. We have a good we have a nice view of torque and how it actually works and why it works. And so we can actually figure out the torque from a number of things as well. So let's say you had a scenario where you have a loop and you have the magnetic field pointing into the page. Let's say that you want current to flow this way. How do we figure out if there's a torque, or if anything, there is a torque? And so, sorry, this is into the page. I said into the page and I wrote out. This is into the page. And so, how do we figure that out? Well, check this out. We know that the force is equal to I L cross B. And if you take each of these segments to be L, and you know where the B field is going, you can calculate the force on each of these. So let's look at the force for each segment. Okay, we'll do it in blue. So the force here and here. Since current's moving to the right, and the B field's pointing into the page, we can calculate, well, let's calculate the force. If my finger points in the direction of L, which is to the right, B field points into the page, then you know that your force points upwards. Awesome. Well, because your force points upwards, you can say that on this other side, this force points downwards. Let's see. Oh, let me do this way. Sorry, let me change the B field, actually. Let's make the B field go this way. So we can ignore these zeros. And then we could say that, okay, let's look at the force. It's IL cross B. L now points in the same direction as the B field. Cross product says that it's the sine of the angle between the two. Sine of the angle of 0 is 0. There's no force. However, here, let's check it out. Here, on this segment, L points upwards, and B field points there, points to the right, so you know that the force points into the page. Likewise here, this force is 0, because once again, it's moving anti-parallel to B, but the angle is 180. Sine of 180 is 0. F equals 0. And lastly, when it points downwards, you put your finger going downwards, magnetic field going into the page, or going to the right, and you know that the force points out. Comes out. And so, awesome. You know that there's no force here and here. And you also know that the net force of this complete thing is 0. Linearly, it's 0. There is no linear force because the two components on this branch and this branch are 0, and this branch and this branch are equal and opposite. So this value is 0. However, there is and might be a rotational force. So if the force points inwards here and outwards here, you could kind of figure out that if you have your axis of rotation go through the center, you could kind of figure it out that, yeah, you're going to apply the force to the right side of this loop, which will make the left side push up. And so the force, because of this magnetic field, will cause it to rotate kind of in and out. Kind of like this, which I will draw in red, kind of like this. points in and out. So you know that it's going to, if you curl your fingers, that the torque is going to point upwards. Torque points upwards because it's rotating because of a force. This force is rotating like that. Consequently, you can figure that out 3 different ways. You know that F, or torque, is equal to R cross F from classical mechanics. If R is the distance from your axis of rotation, R goes here, force goes into the page. If you do R, which points, your finger points to the right, and your force points into the page, you'll see that your thumb, oh hey, points upwards. It points upwards. So you know that the torque points upwards. Likewise, if you're not sure of yourself, you could do the other side, and it's the same thing. R points to the left, force points out, and if you put your finger to the left, your middle finger coming out, then you realize that the torque points out. So it's the same. That's great. That's from a classical mechanics point of view. But what about an electricity and magnets as a point of view? You know that the torque is equal to mu cross B. Well, we can decompose this and say mu is I N A cross B. And A is our area vector. So if you look at the way current's moving, current is moving counterclockwise, which means that I is counterclockwise. A points counterclockwise, then you curl your fingers in the direction of I, where it's going, and you see, yeah, your thumb points out. So A points out of the page, or A or mu points out of the page, points out of the page. Awesome. Well, you know that once again, torque is mu cross B. So let's put it out. If you put your finger pointing out of the page in the direction of mu, and you put your middle finger towards the direction of B, you'll realize that your thumb also points up. If your thumb points up, that means that torque points up as well. So you know that the torque points upwards. So we just did it in 3 different ways. You can look at the forces on the loop, each of the individual forces, and say, oh, it's pushing into the page on one side, pushing out of the page on the other. If I can kind of see me pushing a loop like that across an axis, you'll realize that, yeah, it rotates with torque that points upwards. If you can't see that, then maybe, oh, you know where the forces are, but you know that torque from classical mechanics is R cross F. So you can draw R from the axis of rotation, and you'll see that you get the torque to point upwards as well, if you do the right-hand rule. Once again, if you're unsure of yourself, you can try it with mu cross B. And if you realize that current's going clockwise, counterclockwise, like it was, and like I set it up to be, then it points, yeah. Then mu points out of the page. If it points out of the page, then you put your finger out of the page, you feel going to the right, and you see that your thumb points up. So once again, the torque has to point in that same direction. And so, once again, this was really cool about physics. You could look at it from many different ways and get the same result. And so, this same result can happen no matter what you look at it. You know, you look at it from a classical standpoint. You reason it out. You say there are 2 forces go opposite directions. But about an axis of rotation, then it must torque. Yeah. So once again, it's going to torque like this. Now, going back to the scenario I gave above, the reason why it's going to torque upwards is because the reason why it's going to torque upwards is because it wants to minimize energy again. You want to minimize energy to the point where mu u is equal to negative mu dot b. And the only way you can do this, if the lowest value you get is negative mu b out of this. And you get that if theta, the angle between mu and b, is 0. Well, let's look it up here. That's not the case. You know that mu points out of the board. Mu points out of the board. Because mu points out of the board, you know that it is actually perfectly perpendicular to the B field. Because it's perfectly perpendicular, you know that, yeah, it's going to have to torque to get you this much about energy. And so we can look at it like this. Theta 1, theta 2, tau d theta equals mu b sine theta d theta. You get negative mu b cosine theta, and you started perfectly perpendicular. Perfectly perpendicular means that you moved 90 degrees and you started at 0 degrees. So cosine of 90 is 0. 0 minus negative mu b times 1 is equal to mu b. That is the work. That's the work that we just done. And once again, it's positive, so you know it's going to move in that direction. Okay, well, delta, the work is equal to negative change of potential, which is equal to negative mu b. But let's see if this holds true. If we look at now, delta u is equal to negative mu dot b. This is final. Final minus negative mu dot b initial. Right? So let's look at mu dot b first. It's negative mu for the final is equal to negative mu b cosine. Once again, it's going to go towards the magnetic field. So theta is 0 is equal to negative mu b. Minus a negative is plus, plus mu b cosine. Now, where did it start off? It started off perfectly perpendicular to the B field, since mu points out of the page. This will end up being 90 degrees. Cosine of 90 is 0. So delta u is equal to negative mu b. Well, we just figured out, once again, that's the equal and opposite of the change of work. And so you know that this thing is going to torque, and it has to torque in a way where the magnetic moment is lined up towards the magnetic field. And it does that by moving 90 degrees. And it does that by moving 90 degrees counterclockwise. And we figured that out because, once again, the forces will rotate this thing counterclockwise. The force points in and points out means that the thing's rotating counterclockwise, and you know that the torque points up. If the torque points up, the thing goes counterclockwise. So yeah, go figure this thing is going to move 90 degrees counterclockwise to minimize its energy. And it will do that by telling you that this value right here is negative and the work is positive. Work's positive because the force acting on you gives it. The way I like to think about it is when work's positive, that means that the force that's doing whatever to you does it the way it wants to do. Which means that this magnetic force is doing what it wants to do. It's pushing you towards a lower potential. And you can see that by the potential being negative. So, and that's a good review on torque. And that's how I like to view it. You know, from a physics standpoint, I like to view it as looking at energies and reason through what must happen because things, once again, want to go to a lower potential. Always want to go to a lowest potential. And so that's it. That's all I have for you guys today. You guys have any questions, just feel free to email me or ask me for anything you need.